the um, the application side of linear algebra, and now we're going to be headed towards like the heart of linear algebra, which is a bit more theoretical in flavor. So the past few lectures, the past few homeworks have been very application heavy, finding the norm, finding the angle between two vectors, computing cross products, computing determinants. So it's very computationally involved, right? We're still gonna use computation, but it's now gonna be a bit more abstract. And what do I mean by that? Well, the first thing I'm going to head into are called vector spaces. So I think we are ready for the more theoretical aspect of linear algebra. We've been dealing with matrices for the first 8 lectures, and then we headed towards linear algebra with the more vectorial flavor to it, right? So it's all about vectors and what do we do with vectors and how do we add vectors and how do we envision vectors in 2-dimensional space, 3-dimensional space, the dot product of vectors, projections upon vectors. So it's a lot about vectors. And now we're going to extend that idea of vectors and talk about what are called vector spaces. So up to this point, we've been talking about vector spaces, but we haven't been very explicit. Okay. So what is a vector space? Well, let's begin by saying let V. So we're going to be using a lot of notation, a lot of variables, a lot of different letters. So let V be an arbitrary non-empty this phrase here, non-empty, may seem redundant, maybe like, yeah, why would we talk about something that doesn't have anything in it? But we like being very explicit. And we like saying it's non-empty, meaning that it contains something, at least something, right? Let V be an arbitrary non-empty set of objects with 2 operations defined. And normally we have 2 operations. The first operation is an addition operation, and the second is a multiplication operation. And in particular, it's not just any kind of multiplication, it's a scalar multiplication. Okay. Then the following must hold. If the following axioms, so see, we're going to be taking an axiomatic approach to this. If the following axioms hold, then we call V a vector space. And we call those objects in V we call them vectors. So it's kind of interesting that we've already been speaking about vectors, right, as objects that have a magnitude and a direction. So that's our understanding so far as to what vectors are. And particularly, we've been dealing with vectors in two-dimensional space, three-dimensional space, and then we extended that to n-dimensional space, right? Rn. So it could be r to the 10, which is a vector that has 10 components. So we were looking at it from a geometric perspective. And we just extended it by saying, hey, we have a few more components to the n tuple. But now we're extending this idea of vectors. Vectors are not just vectors that have components. Vectors are objects that abide by these. I'm going to give you these 10 axioms. So if you have a vector, a set of things, set of objects, where you have these two operations defined, addition and scalar multiplication, and if the following 10 axioms are true, then those objects that you are utilizing from this set are called vectors, and this set is considered a vector space. So this sounds very like almost up in the air, right? It sounds like something not really clear or concrete, I would say. So the first one is if I'm going to use a little vector, the little symbol above, a little arrow above to denote vector. So if U and V are in V, then U plus V is in V. I'm gonna do a few things. I'm gonna rewrite this a bit shorthand in a shorter notation. I'm gonna use some symbols. So I'm gonna say if U V is in V. So this little symbol right here just means belongs to. Some of you may have seen this already, maybe in discrete math. But this little like almost like an E looking symbol, this means belongs to or is in. So U and V are in V, then I'm gonna do the same exact thing here. U plus V is in V. Okay, so I'm just gonna use this here notation here. It's gonna be more commonly used. I'm gonna use this symbol a lot more than writing is in, is in, is in. Instead of writing that, I'm gonna use this symbol. Okay, so it's pretty common. Right, this is IE, in other words. Okay. Now this first axiom is called closure. It's closure under addition. Very important property, the closure property. The closure property just means that it's closed. What that means, mathematically speaking, is that if I have two things in this space called V, if I have two things, call them little u, little v. And if I were to add these two things together, the result is still going to be in the set. That's what I'm saying. So if I have an object, two different objects in V, I add them together, and now this sum, whatever I get from adding them, is still going to be in that vector space called V. This is a very important property of vector spaces, and it's called closure property under addition. Okay, that's the first property, axiom, for every vector space. And we'll come back to that again. And then obviously we have things that are associated to addition. This is commutativity of addition. That's expected, right? If you add two things, then the reordering the order of that operation should hold as well. Associativity as well should also hold. So the associativity also holds. Okay, so we got closure, we have commutativity, we have associativity. We also have an identity element. An identity element exists. And particularly, right, I'm going to say an additive identity. And of course, we're going to denote that by 0. So it exists such that v plus 0, 0 plus v equals v. So this is the additive identity, or I should say the existence of an additive identity. So as you can tell, this is much more, I would say, generalized version of what we've been looking at so far. Now we're applying these properties of addition, but now we're extending them to vectors. So we want commutativity of addition, associativity of addition, and the existence of an identity element. Along with that, we have an additive inverse. So every vector V has an additive inverse. And we call this additive inverse negative V, such that V plus negative V or negative V plus V is 0. So we have existence of additive identities, and we also have existence of additive inverses. Okay, we're almost there. We're halfway there. So there's 10 of them. 6. 6 is scalar multiplication now. So if I have a vector, if I have a scalar, so for a scalar C and a vector V, for a vector V in the vectors in the set V, K times V, or I should say C times V is also in V. So this is the closure under scalar multiplication. So this idea of closure appears twice. We have closure of under addition, so the two operations have to be closed, which means that if I add two things in V, then the sum will also be in V, closed under addition. If I have a scalar C and a vector in V, and if I perform scalar multiplication, the result is still going to be something in V. So scalar multiplication is also closed. Okay. So for a scalar again, for a scalar C and VW in V, then we have K of the sum is equal to KV plus KW. So this obeys the distributive property of scalar multiplication. And then a few more things. If C and K are scalars and V is a vector, then C plus K multiplied by the vector V is equal to, obviously, C times V plus K times V. So this also holds. So they look similar, but they're a bit different, right? This is a sum of vectors being multiplied by a scalar, and this is a sum of scalars being multiplied by a vector. But we still have the distributive property hold. It holds in this fashion as well. And then we have associativity. So if we have K times, if we have C times K times V, this equals C times K times V. This associativity of scalar multiplication. And then the last one, we have the existence of multiplicative identity. So these 10 axioms, if it holds for any set, is considered a vector space. Okay. So we went from a very computationally heavy perspective of vectors, and now we're becoming more on a general abstract viewpoint. Okay. Okay, so now let's be a bit more concrete with this, and let's talk about examples of vector spaces. And probably the simplest, and I would say probably the most uninteresting one, is the vector space, the zero vector space. So what is the zero vector space? It's the vector space that contains the only one element. It's a singleton set. A singleton set containing only one element. And if you have a vector space with just the zero vector in it, this obeys all of the axioms of the ones that we just defined. So if you take 0 and then you take 0 again and you add 0, you get 0. So you see how it's a bit simplistic because it obviously obeys all of the axioms about addition and scalar multiplication. So it's closed under addition, it's closed under scalar multiplication, the associativity, commutativity properties of addition work, the distributive property of scalar multiplication works, and the identity and all of the other axioms for scalar multiplication also holds. So that's one of them. Even though it is simplistic, it's just important to note that this exists and that this is an example of a vector space. Okay. And so far, all the ones that we've done is Rn. Rn is a vector space. You can take any vector in Rn and take other vectors. Take two vectors in Rn. And then you can also confirm and a scalar, take a scalar C. So these are the vectors. And this is a scalar. And if you take the n tuple V and the n tuple W and the scalar of C, it also will obey every one of the axioms that we just defined. So all this time we talked about vectors in Rn, we're dealing with vectors in what's called the vector space. So Rn is a vector space, R2 is a vector space, R3 is a vector space. We've been just dealing with it as a geometric simplification, right, of the two-dimensional space and three-dimensional space. And you've heard about this term space before. It's a space, but now we're considering it more generally as a vector space, not just a three-dimensional space, but a R3 is a vector space. Okay. And so I'm gonna introduce a few more things here. There's also a space called R to the infinity, but this is a vector space. And what is this particularly? A vector V in R to the 0 to the infinity is the following. It's a vector that has an infinite number of components. So now that's kind of tricky, right? That's kind of like, now we're headed not to, we're dealing with spaces now that have an infinite number of components to them. I think at one point finding or dealing with things such as things in R5, R10 space, right? Vector space, we kind of still were able to extend this idea of, oh, if we have three components of something in R3 space, then going to the fourth dimension, just adding one more component. And we kind of accepted that. But now we can treat vectors and deal with vectors that have an infinite number of components. These are called infinite dimensional spaces. So linear algebra is not only connected to spaces that have a finite dimensional space, that are finite dimensions, but we can actually deal with things that are infinite dimensions as well. So this idea of linear algebra, again, it extends to something beyond just the physical, beyond just the finite dimension. Okay, so this is also a vector space. What else? Of course, we have M, we have the notation for this is MMN is a vector space. So we've been going from the zero vector space to the n-dimensional vector space, Rn. And then we have R to the infinity symbol here, which is a also vector space where the vectors are all infinite number of components. And now we're dealing with M under subscript Mn is a vector space. And this, what is this? This is the set. This is the set of matrices with M rows and N columns. So it's the set of all matrices. I should say all. So an example of this, an example within an example is M22. What is this? This is the set of all 2 by 2 matrices. So for example, if I have, these are vectors. You can treat matrices themselves as vectors. So for example, if you have a matrix 1, 4, 7, -7, 2, this is comparable to having a vector like this. It's comparable. So M22, this vector space of the set of matrices of 2 by 2 is similar to R4. Do you see that in the structure? It's similar to R4. You can treat it as R4 because you have 4 components within a 2 by 2 matrix. You have 4 components, the same way that an n-tuple in R4 has 4 components. So we can treat this as a vector. We can. We can interpret it as something in R4. Not exactly, but similar. Like I said, the keyword here is similar. Okay, another example of a vector space is F -infinity to infinity. Now, what is this? This is the set of all functions defined on -infinity to infinity. And of course, what are the operations here? What are the operations in this space? It is addition, but this addition is applied to functions. It's a function addition. So what you've seen before, f of g of x, right? This is f of x plus g of x. This is the addition for functions, right? Addition for functions. And then we also have scalar multiplication. C of f of x is equal to c multiplied by f of x. Scalar multiplication for addition for functions. And then we have a little smaller vector space. These are f of AB. These are the set of all functions defined on interval AB. So if you have a defined set AB, then f of that interval represents all the functions that are defined on that set. Those are also vector spaces. So does this make sense? Any questions so far about vector spaces? It could sound all as mumbo jumbo here as of now, but hopefully with a few more examples, and we'll see where this head leads us. So these are all vector spaces, and again, you can take these operations and apply them to functions inside of this space, and it will obey every axiom that we have defined for vector spaces. So let's talk about things, an example, a counterexample that is not. So if these are all vector spaces, what is not a vector space? So an example of a set that is not a vector space. Sometimes it's good to know what something isn't to understand what it is. So what is not a vector space? So let's consider a vector of V being R2, okay? So my set is R2. So R2 in itself is a vector space when you have the operations of addition and scalar multiplication applied, right? So then we're going to define the operations the following. Define the operations. So remember, every vector space has two operations. There's a addition operation and there's a multiplication, scalar multiplicative operation. So suppose we have the regular definition for scalar multiplication, which would be V1 plus V2, sorry, V1 plus W1, comma, V2 plus W2. So suppose we have this is the standard, right? This is the standard addition definition for vectors. Now, what if we have a scalar multiplication? So what if we have scalar multiplication defined in this very strange way? What if we call this C multiplied by V1, right? Which what you would normally think would happen, and then we call this 0. So this scalar multiplication is a bit different than normal. The normal one, the standard one would be CV2, right? That's how we would define scalar multiplication. So you may think, but why are we doing this? This is just an example to show you that these operations, there's some arbitrariness to them. You can create your own operations. It's just that this is standard, right? This is standard way of adding things is adding by component wise, V1 with W1, V2 with W2, but we can also define addition differently. This doesn't have to be the only way to define addition, but this works. So then we utilize it. Scalar multiplication as well. We can define scalar multiplication in this manner. That's perfectly fine because it's an operation. We just created it to be, someone said it, this was so, this is so. So there's a lot of leeway to that. But then the question is, if we were to create this operation, what's the consequences of it? What's the ramifications for this scalar multiplication? Now you see how this is a bit different. Then what's the problem? Obviously, this is closed under addition, right? Because any two things in here will also be in it. But what happens with scalar multiplication, for example? So let my example, in this example here, let call V, call it 2 comma 4, and let W be negative 3 comma 5. And let my scalar be 7. What is U plus V? What is U plus W? It's negative 1 comma 9, right? And then what is C times, sorry, this should be V. What is C times V? What's 7 times 2 comma 4? Well, according to this scalar multiplication, what would that be? That would be 14 comma 0, correct? Is the sum of two vectors, is this still in V? Check. And is the scalar multiplication something in V? It is. So it is closed under addition and scalar multiplication. But what would be the issue? So again, those 10 axioms have to hold. The moment that one of them doesn't hold, then everything falls apart. And that set that we have is not a vector space. So does anybody see what can go wrong? Anybody?
If we like multiply two vectors with different dimensions.
Well, yeah, the thing is though, we're living right now in this space. We're living in R2. So all our vectors will be the same dimension. They'll have two components to them. So we can't, and also when we talk about multiplication, we're not dealing with multiplication of vectors, we're dealing with scalar multiplication. So we have a scalar multiplied by a vector. So our multiplication is very specific. It's scalar multiplication. It's not vector multiplication, which the only vector multiplication that we can think of is dot product. So we're not dealing with dot product, but we're dealing with scalar multiplication. But that's a good idea. But again, we're living in R2. So the operations defined, the way they're defined, they produce vectors that are still in R2, which means that they're closed. But the issue, what's the issue? The issue, if you notice, is the very last axiom. What if I took 1 multiplied it by V? Is this still going to be V as a result? In other words, under this operation, does the scalar multiplicative identity exist? Is there a scalar multiplicative identity? Well, if I were to perform this scalar multiplication operation that the way it's defined, I would have 1 multiplied by 2 comma 4, which would give me 2 comma 0. But this is not V. V is what? 2 comma 4. So no. 1 is not the scalar multiplicative identity. It doesn't work this way because of the way scalar multiplication is defined. Because of the scalar multiplication definition. Does everybody see that? Isn't that more so an issue with the properties? Not with this particular example. The problem is that the last axiom for a vector space is not met having this scalar multiplication defined. The problem is the scalar multiplication, the way it's defined. Because I defined it in this very strange manner, the result is a set that has two operations, but is not a vector space. So the problem is the way that the scalar multiplication was defined here. So the way the scalar multiplication is defined results in having one of the axioms, one of the properties, not being met. Because what's the last axiom? The last axiom is something that you would expect, right? If you have a vector and you multiply by 1, a scalar multiple, you would get back that vector that you have. That's what we would expect. But the problem was that this vector, that this operation was defined in this strange way. Again, I can create various different ways of scalar multiplication. This is not just the only one. There are many others that you can create yourself. But will it be something worthwhile to pursue? Will it be something that obeys the 10 axioms that we've defined? If it does, then it makes sense to look at it and to further investigate what it results in. But this here, we can stop here. Yeah, that's not a, so I don't know what you're really referring to as the property. The property that doesn't hold is this. This is the property for vector space. My thing is, does it hold for this particular example? And it doesn't. For this example. So I'm giving you an example of something that is not a vector space. All the other ones that I've listed here are vector spaces, and you can check for yourself that if I have something, for example, in this space, a function, any function that's defined on the interval -infinity to infinity, and I add it with another function, then I will have all of these axioms hold. That I would have all these axioms being met. And the same thing happens with this scalar multiplication. It just works out for all of the axioms or the properties as you mentioned. But yeah, this is not a property of a vector space. This is a way that a scalar multiplication was defined for this particular example. And in doing so, we created something that's not a vector space. That's all the illustration is trying to say. So we have a vector space and we have two functions defined as such. One of them is the normal way of addition, and this one is some strange way of multiplying. Because normally this would be what? C times V2. But for this example, and just to establish the point, we just made the y value being 0. So every single time we multiply C by V, this becomes CV1 and this becomes 0. So that's okay because why? We can do this and we still get something in V, This is still going to be an R2, so that's okay. And then we can try other axioms that we have. But the problem is that this last one, it doesn't result in having the same vector again, as it should. It doesn't. So therefore, this is not, this vector, the ways to find with the operations is not a vector space. So the conclusion is that V is not a vector space. And this, again, this is due to the above. It's due to the fact that there is no scalar multiplicative identity, which means that there is no possibility that when you take one and multiply it to this vector under the way that the scalar multiplication is defined, under that definition, it doesn't result in getting back V. It gets something that's not V. So therefore, it is not a vector space. It makes sense. Thank you. Great. Great. Like I said, it's helpful to see what's not a vector space so you can understand, oh, wait, so vector spaces are a bit more special to deal with. Not everything can be a vector space. If I just list to you all the vector spaces, then you're like, oh, everything's a vector space. But the moment I say, hey, look, this is not a vector space, then you start to see all the difference between what vector spaces are and what potentially may not be a vector space. Okay. So let me talk about a few more additional properties of vector spaces. So an additional property are things, like I said, that you should expect, right? So if you take U and you multiply it to V, pardon me, if you take 0 and multiply it to V, the result should be what? What should be the result when you apply this kind of scalar multiplication? 0 multiplied by V should give you 0. Oh, and again, this should be a scalar 0, right? The scalar 0. And this is the vector 0. It's not the same. They're different. So we should expect that. What else should we expect? We should expect that if we have a scalar k multiplied by 0, right? If we have a 0 vector multiplied by a scalar k, then we should get the 0 vector again. That's kind of also expected. What else? If I have -1 times a vector v, -1 times v obviously should be what? Negative v. And then lastly, we should get that if k times v is 0, then either k equals 0 or v equals 0 vector. Okay, now the interesting thing is to prove some of these. So we can prove these. So proof of A. What would be the proof of A? I want to show, sorry, I don't know why I wrote that little symbol above. I want to show, what do I want to show? I want to show that 0 multiplied by V is equal to 0. Now, what do you guys think? How do I show this? How would you show this? Now, this would be simple. This would be simple if V was in Rn. Because then you would just say V has n components. You're multiplying by 0 by the scalar multiplication operation, and therefore everything will be result in zeros. So that's kind of straightforward, right? But do you see why this is not straightforward? Well, it's not straightforward because V is not necessarily an Rn. V could be where? It could be in M22 or in M or V could be in M 300 by 500. Or V could be in the vector space F. This could be a function. So you see how the proof for this has to be more generalized. It can't just work for Rn and say, yeah, it works for everything else. Do you see the difference? Do you see why it's a bit more complex? So because it's more complex, because of the fact that V could be any vector in any vector space. So again, V, so let V be a vector in V, but this V is not defined. This is an arbitrary vector space. So for any vector space, take an element in this vector space V. What do we know for sure? So this is when you kind of have to play around with this a bit. Well, what we know is that if we take 0 and multiply it by V, and if we take 0 and we multiply it by V, this is the same thing as saying what? 0 plus 0 times V. Is this agreed? And why is this true? We had the distributive property. Isn't this one of the properties or axioms for a vector space? So see, at this stage, we're dealing everything with the axioms, with the properties that we've established for vector spaces. We're not looking at anything else. We're not looking at what V is. We're not considering it whether it be Rn or if it's the function space or if it's the matrix space. We're not considering what V is particularly. We just assume that V is a vector space. It could be any vector space as long as it is a vector space. And so if that's the case, then this sum here would give us this result because of the distributive property, right? You can distribute the V. And then what do we know about 0 plus 0? Well, we know that 0 plus 0 is 0. So do you guys see this? I'm saying that 0 times V plus 0 times V equals 0 times V. But why can't I just go from here to here? Why can't I just do that? Because we don't know what V is in. We don't know what kind of V vector space we're dealing with. But this is true because of the property for vector spaces holds. This is true here because, of course, when you add two scalars, 0 plus 0, you get 0. And then what? Then what? What else do we know? We know that what? This must have a what? What must this have? There must be an existence of the additive identity. So what must exist? Negative 0 times v must exist. Do you guys understand what I'm trying to do? This must exist. So whatever element this is, so do you see that I still, in this proof, I still haven't established the fact what this equals. I'm just treating this as an object. I'm treating 0 times v as a thing, whatever that thing is. What I'm saying is this thing plus itself gives me this because of the properties under the distributive property that we have for vector spaces. And this equals this because scalars, adding two scalars that are zeros, add up to become 0. Now, these things that I don't know yet, that I'm trying to show what it equals, these two things here, right? These things are all the same. This must have an identity, additive identity. This must exist because it's a vector. It's in a vector space. So if that's the case, then what can I do? What can I do? Can't I say that 0 times v plus 0 times v plus negative 0 times v, doesn't this equal 0 times v minus 0 times v? Oh, that, sure, I'm adding this. Isn't this okay? And if I associate this together, what do we know about additive identity elements when I add them to their counterparts? So if I take some element in the vector space and I add it to its additive inverse, sorry, this should be additive inverse. So if I take some element and I add it to its additive inverse, I get 0, don't I? So this has to equal 0, and it's the 0 vector because these are the vectors. That's the additive inverse. That's the additive identity for vectors. It's 0. And so does this. This also equals 0, doesn't it? Do you guys see that? So this is the additive inverse, and 0 is the additive identity. So if 0 is the additive identity, what should be true about this? If 0 times v plus 0, what does this have to add up to? Since this is the additive identity. If I add anything by the additive identity, I get back the same thing, don't I? That's what it means. So then what do I get? I get 0 times v equals 0. And henceforth, I proved it. This is a very interesting proof because it's not so apparent, even though the result seems very straightforward. This seems like, yes, of course this should be, of course. But then the question is, how do you prove it in its generality for any vector v in any vector space? Then the only thing that we can really go by are the properties of vector spaces. So any questions about that? It seems to be a bit like convoluted for no reason, but this is the way to generalize the proof that anytime you have a vector in any vector space and you scalar multiply it with 0, you get the 0 vector, which is the additive identity. Okay. So again, vector spaces are defined by those 10 axioms. And based upon those 10 axioms, I can have these additional 4 properties. And to prove each one of these properties to be true, I'm going to only utilize the axioms that are already defined for me. And that's what I did here. So as you can tell, it's a lot more theoretical than we normally have had our classes. So now that we have a better understanding of vector spaces a bit more, the next thing to talk about are subspaces. And this is a very important topic. Subspaces. So when we talk about subspaces, we're dealing with vector spaces. We're dealing with subsets of vector spaces. So a subspace, normally we're going to treat uppercase V for vector space, and we're going to treat uppercase W for subspaces. So a subspace, a subset, I should say, a subset W of a vector space V is called a subspace if W is itself a vector space. Under the same addition and scalar multiplication operations defined on V. Again, this sounds a lot more abstract than normal, but you see why these statements are true. So a subset of a vector space V is called a subspace if that subset W is itself a vector space under the same operations that V has. Okay? And what we're going to be interested in is, given a subset of a vector space, what we're going to have to do is be able to determine whether that subset is indeed a subspace or not. So what are the conditions to test? Conditions to test whether a subset of V is a subspace. Now, the good thing about the conditions is that we don't have to go through all 10 axioms. So once we know V is a vector space, then we only have to check 3 things. So the first thing is we have to check whether or not it's empty. And the best way to check that is if 0 is in it. So 0 must be in it. So the first thing we check is 0 in the subspace W. Or I should say 0 must be. 0 vector must be in W. If the 0 vector is not in W or is not in this subspace that we're trying to figure out, if W is a subset that does not contain the 0 element, then it's not a subspace. It will not be a subspace. The second thing that to check is closure under addition. Meaning that if W1, W2 are both in W, then W1 plus W2 must also be in W. That's what it means to be closed under addition. So your subspace must be closed under addition. And if that's okay, if that holds, then you also have to check closure under scalar multiplication. So if we have a scalar, so if C is a scalar, and again, C meaning a scalar, it means that it is just a real number. It's a constant. If C is a scalar and V is in V, then C times V, sorry, it should be in W. So I'm gonna call this W. So if W is in the subset W and C is a scalar, and if you multiply a scalar by a vector in W, then that should also be in W. So if a subset that we're trying to determine whether it's a subspace of a vector space V, if that subset contains a zero element, and if that subset has a closure under addition, meaning that if you add two things in the subset, it's also in the subset again. And if it's closed under scalar multiplication, so if you have something in the subset called W, and you have a scalar and you scalar multiply the scalar with the element in the subset W, and that result also is in W, then we have what's called a subspace. Okay, does that make sense? It may not make much sense because it's a whole bunch of words. You may be thinking, where's the actual computation? Where is the actual concrete examples? So let's see. So again, let's go back to a simple one. If we have a W is the simplest, if W is the zero vector space is a subspace of V. What this means is if you have any vector space V, then the set that only contains a zero vector is always going to be a subspace. Why is it a subspace? Because we showed that the vector zero, if you only contain a set that only contains a vector zero, is itself a vector space because it obeys all the 10 axioms. And if you want to further confirm that this is a subspace of any vector space, well, first of all, does the first condition hold? Well, zero is in it, so zero is the only thing in it, so zero is in it, so one holds. So condition one holds. How about condition two? What if I take two things in W, but the only two things in W are what? Zero, and if you add it to zero, what do you get? You get zero. Is zero in W? Of course it is, because that's the only thing that is contained in W. And then the last one is if you take a scalar and you multiply it by zero, we just showed that if you multiply this by zero, right? What's the result? Well, C times zero will always give me zero. Is zero in W? Of course it is. So this is kind of a pretty simplistic, again, space. And not only is it a vector space, it's a subspace of any vector space. So the zero vector space is always a subspace for any vector space. Okay. What are other subspaces? Um, well, for example, another example of a vector space is any line that goes through the origin. So I'm gonna call this W. W is a line that goes through an origin, the origin. In R2. So W is a subspace of R2. Now, why is that? Why is that? Well, if you take a vector, if you take a line and it goes through the origin, first of all, does it contain the vector 0, 0? So I'm gonna call this W, right? So is W a subspace? How do we determine that? Well, the first thing is 0 in W? Well, the 0 vector, right, is right in the middle, and this line W goes through the origin. So obviously, yes, this holds. Second, what would be the second thing? If I have two vectors, W1, W2, in W, so what does that mean? So if I have a vector here, right? So I'm gonna call this vector W1. And if I have another vector, it's a bit. So if I have another vector, doesn't let me go. So if I call this W2, what happens when I add W1 plus W2? Is this also in W? Remember, that's what it means to be closed under the addition. So if I have a vector W1 and I have another vector W2 along this line, is the resulting vector also going to be on this line? Yes or no? What do you guys say? Yes, right? So then this is also true. So it's closed under addition. Do you see that? Do you see what we're doing? It's closed under addition. Of course it is. If I'm on this, if I'm a vector on this line, I have another vector on the same line. It doesn't matter where that vector is. As long as I'm on the same line, when I add the two vectors, I also have the resulting vector being on the same line. And then if I have a vector and I have a scalar, what is C times W? Is this also in W? So if I have a vector, right, and I scalar multiply it, then I get another vector on the same line, obviously. So again, these three things hold. Then what's the conclusion? Well, since these three conditions hold, then the subspace, then the subset of the vector space R2, this subset is a subspace. And then you go on to say that any line that goes through the origin in R2 is a subspace of R2. So note, any line that goes through the origin in Rn, I'm going to call it R2, in R2 is a subspace in R2. And the key point here is that it goes through the origin. So then a completely fair question would be, what would happen if my subset doesn't? What if I have a line that doesn't go through the origin in R2? And I call this W. Now, is W a subspace? So can anyone answer that? Is W a subspace if the line W does not go through the origin? No, it is not. No, why not? Because 0 is not in W. Obviously, doesn't go through the origin. So the vector 0 vector is not in this subset. If it's not in the subset, there's no reason to mention W being a vector space, let alone a subspace. So having 0 inside the space that you're dealing with, the subset that you're dealing with, is essential. If there is no 0 vector, then there's nothing to speak of in terms of subspaces, vector spaces. You must have the 0 vector. Very important. So any line that goes through the origin is a subspace. A moment that you're not going through the origin, you're not a subspace. Like there's no chance. Okay. Another example. What if I call W the set of all symmetric matrices? The set of all symmetric 2 by 2 matrices. Is W a subspace of M22? We know M22 is a vector space, right? It's the set of all 2 by 2 matrices. I defined so think about this. I know this, so this is where the theoretical aspect comes into play, right? Because we're saying it's the M22, right? M22 is the set of all 2 by 2 matrices. So every 2 by 2 matrix that exists, we clump that together and call that M22. Obviously, there's an infinite number of such matrices because every component has an infinite number of choices. You have an infinite number of choices for those entries, and there's 4 of them. So there's an infinite number of matrices that are in this set. So this set is an infinite size. Now, what we're going to do is we're going to take of that infinite size, we're going to take a smaller subset, which deals with only what? Only the symmetric ones. Do you guys remember what symmetric means? What is symmetric?
Matrix. Oh, sorry, a matrix and its transpose are identical.
Correct. So A transpose equals A. Those are the symmetric matrices. So take all the symmetric matrices that are 2 by 2. And the question becomes, is that new subset of the original vector space, M22, is that new subset W, is that a subspace of M22? Well, then what's the first thing we have to figure out? Is 0 in it? Well, what is the zero vector in M22? What would be the zero vector in M22? It would be, right, it would be the zero matrix. Again, this is going to be not the vector itself. So we're treating matrices as vectors now in its general sense, though. But in the world of matrices, we're dealing with matrices. So this is really going to be what? 0, 0, 0, 0. Is this in W? Obviously. Why? Why is it in W? Because the transpose of the zero matrix is 0. Obviously. Do you see that? So some of these things are obvious. You just have to show it. Second, so I'm gonna use capital letters for this. So if A and B are in W, what does that mean again? If A and B are in W, that means that if I have two symmetric matrices, is the sum, is A plus B also in W? In other words, if I have two symmetric matrices and I add them together, will the result still be symmetric? So do you see how we using this generalization and applying it to this particular example? So if A and B are in W, then what? A transpose equals A, B transpose equals B. The question is not whether this is true. This is already true. The question is A plus B transpose, does this equal A plus B? That's the question. That's the question. And does A plus B transpose equal A plus B? If you say yes, prove it. If you say no, tell me why. Give me a reason why. Well, if you remember one of the properties of transpose, right? A plus B transpose, what is A plus B transpose? Doesn't this equal A transpose B plus B transpose? Do you guys remember that? So A plus B parentheses transpose equals A transpose plus B transpose. But then what is A transpose? It's A. And what's B transpose? B. So yes. So A plus B transpose is in W. Do you guys see what's going on? So A plus B is in W. And then what's the last thing? If A is in W, C is a scalar, then what? So if this is true, is C times A, is this also in W? Right? So if A is in W, then what's true? A transpose equals equals A. So is C times A, does this equal the transpose? Does this equal C times A? Does it? Well, it does. C times A transpose. The transpose only affects it only really affects the matrix, not the scalar. So then this is really the same thing as C times A transpose. But what is A transpose? C times A. So this is also in W. Check. So then what do we say? What's the conclusion? My conclusion is what? The set of all 2x2 matrices, the set of all symmetric 2x2 matrices, and we said this entire thing, we call this entire thing W. The set of all symmetric matrices W is a subspace of what? Is a subspace of M22. So again, we had to go through the three conditions for subspaces. And all we're doing is we're trying to figure out the same question. It's just that the application or the manner in which we show whether these questions hold or the answer to these questions will change depending upon the way W is defined. You see how W here was a line that goes through the origin? And here W was a set of all symmetric 2x2 matrices. And this W depends on the vector space you're dealing with. The vector space here was what? R2. That's a vector space. The vector space here is what? M22. So of those vector spaces, the smaller subsets are those smaller subsets in itself a vector space. In other words, are they subspaces of the vector space? Are they? Well, they have to check these out. If these are checked, if these three conditions are checked out, then it is a subspace. If they don't, then it's not a subspace. So I'm going to talk about a few other subspaces. So let W be the set of all continuous functions. So then the question is W a subspace of F? Remember, F is the F negative infinity to infinity is the set of all functions. It's the set of all functions defined on negative infinity to infinity. So W, I defined it as a subset of that. They're the set of all continuous functions. So then what would be the question? First, does zero exist in W? And again, this zero vector in this general sense would be what? In the space of functions. No, not f of 0. F of 0 is you're defining your f of 0 is the function defined at x equals 0. But what is 0 as a function? Where you're dealing with the set of all functions defined on negative infinity to infinity. So it has to be, so this has to be f of x, right, equals what? 0. Do you see how this is the 0 function, quote unquote? Why is this the 0 function? Because anything you plug into x gives you 0. Yeah, it's the function that results in 0, right? It's very similar to, this idea is very similar to the matrix 0. What's the 0 matrix? Well, everything has zeros in it. What's the 0 function? Well, it's the function that gives you 0 every single time for anything, for any value of x. So is 0, so the question is this 0 function in W? In other words, is the 0 function continuous? And you have to remember, what does it mean to be continuous? Well, if you graph this, what does this graph look like? Isn't it just the x-axis? Right? It's the constant function 0. So isn't a constant function that's just a straight line from negative infinity to infinity, isn't that always continuous? So yes, this is always continuous. obviously. So if it's continuous, then yes, this is in W. So yes, this is in W. Do you guys see this? You have to like expand your brain a little bit more. Now the question is, okay, good. So the zero function is inside my subset W because it is continuous. Now, suppose I have two functions, f and g in W. If they're in W, what does that mean? F is continuous, g is continuous. If I have two continuous functions and I add them together, is it also continuous? Yes. If you have a function that's continuous, another function that's continuous, you add those two continuous functions together, you get a continuous function as a result. So yes, it's a theorem, right, in calculus. F plus G is continuous. And what if the next thing? If F is in W, C is a scalar, is C times F also in W? So if I have a scalar function F, if I have a continuous function F, and I multiply a continuous function by a scalar, will the result still result in a continuous function? And the answer is yes. Is this true? Yes. Again, this is a calculus question. But you see how we're coming back to vectors? So then what do we say? What's the conclusion? W is a subspace of F. Well, W is a subspace of, yes, it is. So the set of all continuous functions, which in this case was W, is a subspace of F, which is the space of all functions defined at negative infinity to infinity. And what we're going to do, note that C1 negative infinity to infinity is that set of all, oh no, just C, sorry, C. C is a set of all continuous functions. Yeah, so the third statement that we're dealing with, right, is whether or not if you have a function in our subset W and a scalar, if you multiply that function by the scalar, is that still going to be in W? In other words, if you have a continuous function and you multiply a continuous function by a scalar, is the result also going to be continuous? So the answer is yes. If you have a continuous function and you multiply that continuous function by a scalar, the result will still be continuous. Multiplying a continuous function by a scalar does not get rid of its continuous or its continuity property. It just remains to be, it remains continuous. And so because this subspace, because this subset of all continuous functions of this vector space has these three conditions that are met, then we say that the set of all continuous functions is indeed a subspace. And in particular, we have this notation for this set. So the set of all continuous functions is this set called C comma negative infinity to infinity. So take all the continuous functions that ever exist that's defined at negative infinity, infinity, take all of them, put them all together, that's a subspace. Okay. Interesting, huh? Okay, and I'm going to show you a few more. CM negative infinity to infinity is the set of all continuous, is the set of all functions with m, what is it? Continuous derivatives. And Cm negative infinity to infinity is a subspace. Subspace of F. So what this is the set of all functions whose, if you take the derivative m times, every one of those derivatives that you take, that you found, every m derivative that you get is continuous. So for example, what would be in here, something in here, an example would be if you have a function x to the m power, you can take m derivatives, right? Actually, you can take m plus 1 derivatives, but you can take this polynomial, this one term this power function, and you take m derivatives of it. For every derivative that you find, you get a new continuous function. So all of those functions that are whose derivatives, you can take m of them, and each one of those derivatives is continuous. They're in this space. That's what it means to have m continuous derivatives. And that, in this space itself, is a subspace. And you can check that out for yourself. It's very similar to the argument for why continuous functions, the set of all continuous functions is a subspace. And then we have this polynomial space. The set of all polynomials. So P to the subspace infinity. This is the set of all polynomials. And remember, just recall what a polynomial is. A polynomial is something that looks like this. And A naught, A1, all the way to AN are real numbers. And N, and the exponents, right? The exponents are non-negative integers. That's a polynomial. If you take the set of all polynomials, you get a subspace. So P is a subspace of F. So take all the functions that are defined on negative infinity to infinity, and a subset of those are called polynomials. Because of course you have other kinds of functions. You have exponential, you have trigonometric, you have logarithmic. So those functions are in here. But this defines only polynomials. And we can get even more specific. We can get more specific. We can get Pn. Pn is the set of all polynomials with degree less than or equal to n. So that's also a subspace. Pn is also a subspace. is a subspace of F. We talked about polynomial spaces just one time. I don't know if you guys remember that one example that we used to find a linear transformation, and we had a polynomial being a polynomial space to another polynomial space, right? So now we're going to go back to that example, but more generality. So Pn, pardon me, my dog, he just barks. So Pn is a subspace of F, and it's the set of all polynomials with degree less than or equal to n. So for example, what is P2? P2 is the set of all polynomials with degree less than or equal to 2. So what is this set going to look like? What is P2 going to look like? It's going to set of all, it's going to be the set of all expressions that look like this: ax squared plus bx plus c, such that a, b, and c are real numbers. Pardon me for that interruption. So in P2, for example, P2, you can also have linear functions, which are polynomials of degree 1, and you can also have constant functions. Okay, so that includes all the polynomials that have degree less than or equal to 2. Does that make sense? So anything that has a higher degree, 3 or above, are not in P2. But you can have a smaller degree than 2, and that's still going to be in P2. Okay. Now, so we talked about polynomial spaces being vector spaces, subspaces. We talked about functions, function spaces. We talked about matrices, spaces. We talked about Rn subspaces as well. So there's a lot of different subspaces that we're dealing with. And now there's one more that I would like to talk about, which is solution spaces. Solution spaces of homogeneous systems. So what is a homogeneous system again? Remember, it's a system where all the equations equal 0, right? And we can treat this as a matrix equation. So AX equals 0, right? It's this matrix equation. So what is a solution space? A solution space is the set of all vectors that satisfy the homogeneous system. In other words, it's the set of all x such that AX equals 0. And I'm gonna call this W. So again, W is the set of all such vectors whose left multiplication of x onto A is 0. this set here is a subspace. W is a subspace of Rn. The moment we talk about matrices, we're in an n-dimensional space. Remember matrices? Recall that matrices represent linear transformations. And so if my A is an n by n matrix, then I have what? Then my transformation T goes from what? Rn to Rm. Remember this? So in this case, W is a subspace of Rn. Now, how do I prove that? So show. How do I show that W is a subspace of Rn? So what's the first step? Is the zero vector in W? So is plugging in a zero into this matrix equation, does this give me zero? Well, obviously, yes, doesn't it? If I take A and I multiply by the zero vector, don't I get zero? So yes, this checks out. So far, so good, right? Secondly, if V and W are in W, is V plus W also in W? What does it mean for V and W to be in W? It means that I take A and I multiply it by V, and I get what? I get zero. That's what it means to be in W. I'm saying V is in W. And it also means that A times W also gives me zero, doesn't it? So I know this is true. I know. Now, is this enough to show that A times V plus W also gives me zero? That's the question. Because if this does give me zero, then this has to be in W. That's what it's defined. That's how we define the vectors. It gives me something zero. Now, is it true? Well, what do we know? We know the operations and the properties of matrix multiplication. We can also distribute. We have the distributive property. So we can write this as A times V plus A times W. But we just showed that A times V is what? 0 plus 0. But 0 plus 0 is what? 0. So then what do we say? V plus W is in W. Do you guys see that? So the second condition holds. And then lastly, what's the last one? If V is in W and C is a scalar, is C times V also in W? Well, again, I know that A times V is 0. I know that. So what happens is A times C times V, is this also give me 0? Does this also give me 0? Well, C is a scalar, right? By matrix multiplication properties, I can take the scalar and place it out in front. I can change the order because it's a scalar. I can't change the order of matrix multiplication, but I can change the order of scalar multiplication. So I have this instead. But what's A times V? According to the definition of V being in W, it means that this is 0. C times 0 is what? 0. So what does that mean? That means that C times V is in W. Do you guys see the argument, the way this is, how it's going from 1, 2, and 3, how we're applying what we know to what we want to show, whether it's true or not? And so once the 3 conditions hold, then what do we say? We say that W is a I should say the solution space of AX equals 0 is a subspace of Rn. All right, guys, so I will stop with this last example.